According to the National Electrical Code Section 210.19a, branch circuit conductors must have an ampacity not less than the maximum load to be served. NEC Section 210.20 states that circuit conductors must have an ampacity not less than the non-continuous load plus 125% of the continuous load. These code sections indicate that circuit conductors, including neutrals, must be sized to carry the load current. In a single-phase circuit, the neutral conductor carries the return current for the circuit. Ohm's law is expressed as I equals volts divided by resistance. Vector analysis for a balanced single-phase circuit, the neutral current is equal to the sum of the phase currents multiplied by 1 divided by the square root of 3. These equations demonstrate that the neutral conductor carries current in a single-phase circuit. NEC Section 310.15b3 ATWO states that conductors installed in raceways shall have an adjusted ampacity determined by using the values of Table 310.15b3. Table 310.15b3 provides adjustment factors for conductors in raceways based on the number of conductors. For 10 conductors in a raceway, the adjustment factor is 0.5. Therefore, the number 12 American wire gauge conductors in the conduit must be derated to 12 amps times 0.5, which equals 6 amps. NEC Section 250.118 states that conductors shall be installed so as not to damage the grounded conductor and shall be secured to the device by an approved means. This code section requires that grounding conductors be installed separately from other conductors. Based on the code perspective, Ohm's law, and vector analysis, it is clear that the neutral conductors in the scenario are current carrying. Therefore, the following actions are required. Firstly, install separate neutrals to limit the number of conductors in the raceway to 10 plus a ground. Secondly, derate the number 12 American wire gauge conductors in the conduit to 6 amps. And thirdly, install a separate number 12 American wire gauge ground wire for each circuit. Let's delve deeper into each of these aspects, starting with the role of the neutral conductor in a single-phase circuit. The neutral conductor serves as the return path for current in a single-phase electrical system. In an ideal scenario, with perfectly balanced loads, the neutral conductor would carry minimal current. However, in reality, loads are often unbalanced, leading to current flow in the neutral conductor. This current is a direct consequence of the difference in current demand between the hot wires of the single-phase circuit. Ohm's law, a fundamental principle in electrical engineering, provides a clear explanation for this phenomenon. The formula I equals volts divided by resistance dictates the relationship between current, voltage, and resistance in a circuit. In a single-phase circuit, the voltage is typically constant, so the current is directly proportional to the load's resistance. When the loads on each hot wire are unequal, the resulting current imbalance necessitates a return path through the neutral conductor. Vector analysis offers another perspective on neutral current, particularly in three-phase systems. While the initial scenario described a single-phase circuit derived from a three-phase panel, understanding the behavior of neutrals in three-phase systems provides valuable context. In a balanced three-phase system, the currents in each phase are equal in magnitude and 120 degrees apart in phase angle. Due to this symmetrical arrangement, the neutral current theoretically cancels out to zero. However, in practice, perfectly balanced three-phase systems are rare. Uneven loading across the phases results in a non-zero neutral current. The formula for calculating neutral current in a three-phase system, I sub n equals I sub a plus I sub b plus I sub c multiplied by 1 divided by the square root of 3, illustrates how the individual phase currents combine to determine the neutral current. This formula is derived from vector addition of the phase currents, taking into account their phase angles. Now, let's turn our attention to derating, a critical aspect of conductor sizing that ensures electrical safety and prevents overheating. The National Electrical Code mandates derating adjustments when multiple current-carrying conductors are installed in a single raceway, such as a conduit. The rationale behind derating is that closely packed conductors generate heat, which can raise the conductor temperature above its rated insulation temperature. Excessive heat can damage the insulation, leading to short circuits, ground faults, and even fires. Table 310.15b3a in the National Electrical Code provides specific derating factors based on the number of current carrying conductors in a raceway. For example, as stated earlier, with 10 current carrying conductors, the ampacity of each conductor must be reduced to 50% of its original value. In this scenario, the number 12 American wire gauge conductors, which typically have an ampacity of 20 amps when used individually, must be derated to 6 amps due to the presence of 10 conductors in the conduit. This derating calculation highlights the importance of considering the combined effect of multiple conductors on the overall thermal environment within the raceway. It is crucial to consult the National Electrical Code tables and perform the necessary calculations to ensure that conductors are properly sized and derated for safe and reliable operation. Finally, let's examine the requirements for grounding conductors, which play a vital role in protecting against electrical shock and equipment damage. Grounding conductors provide a low impedance path for fault current to return to the source, allowing overcurrent protective devices such as circuit breakers or fuses to quickly trip and interrupt the circuit. This rapid interruption minimizes the duration of the fault and reduces the risk of electric shock or fire. The National Electrical Code specifies that grounding conductors must be installed separately from other conductors and must be securely connected to the equipment grounding system. This separation ensures that the grounding conductor remains effective in providing a dedicated path for fault current without being compromised by other conductors in the raceway. In this scenario, the requirement to install a separate number 12 American wire gauge ground wire for each circuit emphasizes the importance of providing a dedicated grounding path for each individual circuit. This ensures that each circuit has its own reliable means of clearing faults and minimizing the risk of electrical hazards. In conclusion, the scenario highlights several key aspects of electrical installations, including the role of neutral conductors, derating requirements, and grounding practices. By adhering to the National Electrical Code and applying fundamental electrical principles such as Ohm's law and vector analysis, it is possible to ensure safe, reliable, and compliant electrical systems. The requirement for separate neutrals arises from the need to manage current flow and prevent overloading of the neutral conductor. When multiple circuits share a single neutral, the combined current from those circuits can potentially exceed the neutral conductor's ampacity, leading to overheating and potential fire hazards. By providing a dedicated neutral conductor for each circuit, the current is limited to the individual circuit's demand, ensuring that the neutral conductor operates within its safe capacity. The derating of conductors, as previously discussed, is crucial for preventing overheating and maintaining the integrity of the insulation. The number 12 American wire gauge conductors, even with their normal ampacity of 20 amps, cannot safely carry that much current when bundled together in a conduit with other conductors. The heat generated by the conductors needs to be dissipated, and the derating factors in the National Electrical Code account for the reduced heat dissipation capacity in such installations. The requirement for separate grounding conductors is paramount for safety. Grounding conductors provide a low impedance path for fault currents, allowing overcurrent protection devices to quickly clear faults and prevent electrical shock hazards. Sharing a single grounding conductor among multiple circuits can compromise the effectiveness of the grounding system, potentially delaying fault clearing and increasing the risk of electrical shock. By implementing these measures, separate neutrals, conductor derating, and dedicated grounding conductors, the electrical system is made safer, more reliable, and compliant with the National Electrical Code. The 208 volt/120 volt system is a common three-phase electrical service found in commercial and industrial buildings. It's important to understand the characteristics of this system to properly apply the National Electrical Code requirements. The 208 volts refers to the phase-to-phase voltage, which is the voltage measured between any two of the three hot wires. The 120 volts refers to the phase-to-neutral voltage, which is the voltage measured between any hot wire and the neutral wire. This configuration allows for both 120 volts loads such as lighting and small appliances, and 208 volts loads such as HVAC equipment and machinery to be served from the same electrical panel. When dealing with a 208-volt/120-volt system, it's essential to consider the impact of unbalanced loads on the neutral conductor. As mentioned earlier, unbalanced loads can cause significant current flow in the neutral conductor, which necessitates proper sizing and derating of the neutral conductor. The National Electrical Code provides specific guidance on how to calculate the neutral load in a three-phase system, taking into account the potential for unbalanced conditions. In addition to the neutral conductor, the grounding system in a 208-volt/120-volt system is also critical for safety. The grounding system provides a low impedance path for fault currents, which helps to minimize the risk of electrical shock and equipment damage. The National Electrical Code specifies the requirements for grounding electrodes, grounding conductors, and equipment grounding conductors in a 208-volt/120-volt system. It's important to ensure that the grounding system is properly installed and maintained to provide effective protection against electrical hazards. The use of 3/4-inch electrical metallic tubing, or IMT, as the conduit in this scenario raises questions about conduit fill and conductor spacing. The National Electrical Code specifies the maximum number of conductors that can be installed in a given size of conduit. This limit is based on the cross-sectional area of the conductors and the internal area of the conduit. Exceeding the conduit fill limits can make it difficult to pull the conductors, damage the insulation, and reduce the heat dissipation capacity of the conductors. In addition to conduit fill, the National Electrical Code also addresses the spacing of conductors within a raceway. Proper conductor spacing is important for preventing overheating and ensuring the insulation is not damaged. The National Electrical Code provides guidelines for conductor spacing in various types of raceways, including EMT. When installing conductors in EMT, it's important to follow the National Electrical Code guidelines for conduit fill and conductor spacing to ensure a safe and reliable installation. The use of number 12 American wire gauge conductors in this scenario is another factor to consider. Number 12 American wire gauge conductors have a certain ampacity, which is the maximum amount of current they can safely carry. The National Electrical Code specifies the ampacity of conductors based on their insulation type and temperature rating. When selecting conductors for an electrical installation, it's important to choose conductors with an ampacity that is sufficient to carry the load current, taking into account any derating factors that may apply. In this case, the number 12 American wire gauge conductors have been derated due to the number of conductors in the conduit. It's important to ensure that the derated ampacity of the conductors is still sufficient to carry the load current. The National Electrical Code is a comprehensive set of standards that govern the safe installation of electrical systems. It's important for electricians and other electrical professionals to be familiar with the National Electrical Code and to follow its requirements when designing and installing electrical systems. The National Electrical Code is updated every 3 years to reflect changes in technology and best practices. It's important to stay up to date with the latest edition of the National Electrical Code to ensure that electrical installations are safe and compliant. In addition to the National Electrical Code, there may be local codes and regulations that also apply to electrical installations. It's important to check with the local authorities to determine if there are any additional requirements that must be followed. A combination of National Electrical Code knowledge, understanding of electrical principles, and adherence to local codes is essential for ensuring safe and compliant electrical installations.